back to what I said about 2 weeks ago was we are working our way up to being able to find out how to calculate what power is equal to, okay, and how it affects us when it comes to mom and dad's hydro bill and whatever else. So this is the unit that we start looking at. How do you calculate power, and then how do we calculate the costs that are related to power? So it all starts with a work formula. So a number of these formulas are all going to start with one formula in particular, and then we work off of it depending on what you're given. Okay, now you get all of these formulas, but let's see where they come from. 1 joule of work is done when 1 coulomb of charge is moved through a potential difference of 1 volt. So originally we talked about work being done to move a point charge over a given distance and changing its potential. So work is equal to Q times V. We initially started all of this with charge, but then we said, well, that doesn't help us get to our power. Well, it does actually help us get to our power, but it doesn't actually help us calculate anything right away. So this all began by finding out what current was. And what was current? Amps. But what was it?
V divided by R.
No. Before that, where did we all start with this? What is it that actually moves through the wires? Electrons. But how do we measure the electrons? What do we measure them in? In what? Coulombs. We measure their charge, correct? So we get the amount of electrons. We take them, find out what the charge is on the electrons, and then we divide it by the amount of time it takes to go through there. So I is equal to Q over T. This is where we began the last unit, right? We found out what current was by taking work is equal to Q times V, but current was equal to Q over T. Now, if I do a substitution here, I can come up with a different equation, all right? And that is this. Let's take and solve for what Q is here. So what is Q equal to here?
I times T.
I times T. That's pretty straightforward, right? Just multiply the T up to that side. Now, if I substitute that I times T in for Q in the work equation, I end up with V I T. Okay? Work is equal to V times I times T. So there's equation number 1. If you are given your potential difference, if you're given your current and the amount of time that it's flowing for, you can calculate the amount of work being done in the circuit. All right? And from there, all right, we look at using Ohm's law. What was Ohm's law again? E is equal to IR. Right? And let's now introduce resistance into this. So if I know the resistance, can I then get work? So work is equal to, if I substitute this in for V here, what am I going to get? I squared times R times T. Awesome. Okay, I squared R T. Okay, so far? So here's something brand new to you. This is on the second page. 18.3. We have been discussing joules a little bit up to this point. So what are joules? Well, Joule's law says that the heat developed in a conductor is directly proportional to the resistance of the conductor, the square of the current, and the time the current is maintained. Well, directly proportional to the resistance, the square of the current, and the time it's maintained. So if each of these increases, so does the work. This is what we refer to as Joule's law, which was actually right there. Okay? What do we measure work in? Measure work in joules. So work is equal to I squared RT. And we measure work in joules. There is another form in which we can use this. And that is this. Work is equal to, and this is brand new to you, J times Q. What is Q again? Actually, I gotta make this a big Q, my bad. Well, it is not a little q. It's not a little q. It's a big Q, which means it can't be coulombs. It can't be charge. So what is it? It's called heat. The quantity of heat. So to look at this equation here, work measured in joules. J is what we refer to as Joule's constant. And Joule's constant is 4.19 joules per calorie of heat. Now we often talk about calories. How many calories do we intake? How many calories do we lose? Well, what we're essentially talking about isn't the actual food, it's the heat, it's the energy that we get from it. Okay? So yeah, it does somehow relate back to mass, right? But calories, in terms of what we do in physics, is what we refer to as heat, or heat energy. And Q, the quantity of heat, is measured in calories. Okay? Any questions so far? So then how is it if I wanted to solve for heat now, what would Q be equal to in that equation? J over W? W over J. W over J, we agree? Yeah. So if that's the case, and we referred, oh sorry, that's not right. And we referred to work using Joule's law, this actually becomes I squared RT over J, and that is the quantity of heat. Q. So to find the amount of heat, okay, how many of you taking chemistry or are taking chemistry? Just the 12s, 11s? You guys are done. You've done some chemistry? Or doing it right now? Next semester. Okay, so just the 12s have taken chemistry so far. We talked about heat energy in chemistry. So exothermic and endothermic reactions, right? What's happening? Heat's given off, heat is taken in. You remember this? Okay? So what that is that's calories. You take in calories, you give off calories. When you eat, you take in calories. When you exercise, you give off calories. Or you expel them, right? Or do something with them. Okay? So heat energy is measured in Q, and we calculate it by taking the amount of work done and divide it by the joules of 4.1 joule and 19 joules for every calorie. Well, there's a secondary way in which we find heat energy, and it's the one that we use more often in chemistry, and that's Q is equal to mc delta T. M is your mass. C is your specific heat constant. And delta T is your temperature. This is how we find heat when we are looking at how much heat is required to raise the temperature of a substance. Not every substance heat changes at the same rate. We all agree, right? Water does not heat at the same rate as oil. Fair enough? So then, when we take the mass of the substance and we multiply it by the specific heat constant, that'll be found on a chart. Each substance has an X amount of heat required to raise 1 gram of that substance 1 degree Celsius. So, in other words, if I'm looking at units here, the units for mass is grams. Yes, we do kilograms all the time, but I'll get to that in a minute. Right now, I'm going to keep it as grams for now. And that's because our chart at the back, the units for the specific heat constant is the amount of calories required to raise 1 gram of a substance 1 degree Celsius. So the specific heat constant is given to you as calories required to raise the temperature of 1 gram of a substance 1 degree Celsius. That's what we call the specific heat constant. And what do we measure temperature in? Degrees Celsius. All right. Now it gets more complicated than that, because not everything stays in the state that it's in. For example, outside today. If you took a glass of water outside today, what's eventually going to happen to the water? It's going to freeze. So its state is going to change from a liquid to a solid. Agreed? Well, in order to change from a liquid to a solid, you need an X amount of heat on top of what's already required to change the temperature. So what we have is we have latent heat of fusion, which changes a liquid to a solid. And then we have latent heat of vaporization. Well, what do you suppose that does?
Changes from liquid to a gas.
Liquid to a gas. So if I were to boil water, that begins, it begins at room temperature, right? And once it hits its boiling point, it starts to steam. It vaporizes, right? So therefore, you're changing the state of it. Well, once you hit that boiling point, there's an excess amount of heat required to change the state from liquid to solid, or sorry, liquid to gas. And that's called latent heat of vaporization. And so that is also given on the same chart in the back of the book as the specific heat constant. So when we get going in the questions, we'll talk about that. Okay? So what is Q then? Q is the amount of heat required. The amount of heat. We measure the amount of heat to do a variety of things. If, let's say I take a hot plate. Everybody's seen a hot plate before, right? Okay. And I set a glass of water on that hot plate. What's happening is I'm going to use the current, and I'm going to have some resistance because the hot plate is metal, so there's going to be some resistance in there. It's going to take an amount of time in order to heat that water until you get to the desired temperature. So let's say hypothetically it's the boiling point. So The hot plate's going to provide amount of heat, Q, in order to change the state of this from liquid to a gas. So the water itself, though, is going to require a certain amount of heat energy in order to change or heat up and then change from a liquid to a gas. So there's two processes happening. The hot plate providing heat energy, and we solve that by taking I squared RT over J. Or if we know V, we could use VI T over J. Depends what's given to us. Okay, we're going to look at this in the physics lab in next week sometime. And then the second process is the actual water heating up. And to find out how much heat is required for the water to heat up, I take the mass of the water in the beaker or a glass or whatever I'm using. I find out what the specific heat constant is. Well, it's 1 for water. I need 1 calorie for every gram to raise it 1 degree Celsius. And then I need to know how much temperature I want to change. So if I start at room temperature, approximately 20 degrees, it may need to get to 100 degrees before it changes its state, correct? Boiling point, 100 degrees Celsius, yeah? So then there's going to be a certain amount of heat energy required to raise the temperature of the water. Well, where do we get the heat energy for the water to heat up? From the hot plate, which provides this. So what we eventually start doing, this chapter is called Heating and Chemical Effects, because we're heating things and then we're watching chemical changes happen. Even a liquid to a gas or a solid to a liquid or liquid to a solid, that's chemical change. It's a physical change, but it's you're changing the chemistry of it. Okay? So we want to find out how efficient our hot plates are. So to do that, I find out how much heat's required to raise the temperature here. I divide it into how much heat is being given by the hot plate. And then I can find that as a percentage. It's called this efficiency, heating efficiency. Okay? So let's look at a question on here. Now, this section is new to everybody. It's going to require you to do the questions the same way we did the kinematic questions, where you write out all your given information on the side, and then you work with the equations given to you. This one's a lot more difficult because there's a lot more variables in play. So you have to really do a good job of finding out what the information is given to you and write it down. This section, we're going to use resistivity more often than what we did in the last section. So we need to remember to use the resistivity constant, use the chart in the back of the book, using the wire gauges and the whole bit. So here it is. The heating element of a percolator has a resistance of 22 ohms. Get your papers out, get your calculators out, and let's do this. It's designed to use across a 117 volt circuit. How long will it take to heat 1 kilogram of water? Now I'm going to change that. And I'll explain that after. So I'm going to change it to 1,000 grams. I'm not going to work with any kilos yet. At 20 degrees Celsius to the boiling point of 100 degrees Celsius. So what's my change in temperature? 80 degrees Celsius, right? Assuming there's no loss of heat to the surroundings. Okay. So this is what I'm given right now. How do I find the amount of heat given off by the percolator? The Q for it. What was the equation for it? Okay, but do I have a W up there? No. What do I have up there?
We have
What was the other equation? After you went to W over J, what did we change it to? I squared R T over J.
But we only have an R and T.
But we can get an I
We couldn't get I. How can we get an I?
because we have a voltage and we have a resistance.
Right.
Voltage divided.
But you're absolutely correct, Dylan.
Mhm.
I can. It's V equals IR, right? That's where you're going with?
Mhm.
But what if I did a substitution? Instead of using I in the equation, because I don't have it, what is I equal to in Ohm's law? I is equal to, what is it? V over R. That's right, Cooper. V over R. Correct? So if I substitute this into the equation instead of I would get V over R squared R T. You agree?
What's it squared?
Because it's I squared R T.
But we have to
Just
do
wait,
that.
just wait. Just hold on a second, please. We all agree with this? Is that what it would look like if I substituted V over R in for I there?
Yes.
Yeah? Now, I'm not saying you can't get the current. It would be easy to get the current here. And that's what they do. But I'm showing you that there's another alternative. And then this is all over J, correct? Okay. So V squared. R squared's on the bottom. R is up here. So it would be V squared T over RJ. This is squared, right? But this R divided by this R squared leaves you with one R on the bottom of the fraction. It's a little confusing here. Now don't write this down. Don't write this part down.
What about-
Okay? So that's what I can do. Instead of using VIT, I can use this, V squared over R, JT, whatever. Okay, so that's a possibility. But it's probably easier for us. Oops. Knowing that, it's just to find I here. So let's do the first thing we do. 117 divided by 22. Give it to me in 3 decimal places. 5.318 becomes our amps, right? Okay, so in that equation right now, what do I have for information? I have my I, my R, I don't have my T.
Oh, no, it's your 80. No, it's your 80. That's your-
What else do I have?
We don't have J.
Just in that equation. Do you see him in that equation? So I don't need it yet. What else? What do I have? Lexi, you said it.
We don't have, I don't know.
Wait a minute.
I think I said we don't have J.
But we do have J. We do have J. It's a constant, 4.19 calories per,
Oh, yeah.
right? Okay? So I have, right now, I have R, I have J. Do I have Q?
No.
No, I don't. So I also don't have time, which is what I'm looking for, right?
Yes.
So far, I don't have enough information to solve this. Well, what is this percolator heating? Pardon me? What is it heating?
Water.
It's heating water, is it not?
Yes.
So how can I find out the amount of heat energy for the water? Q is equal to MC delta T. Well, what do I have in this equation? M and T, and I can get C from a chart. So I actually have all of Q for this. Well, this Q and this Q are the same thing. They're both heat energies. So what do you suppose I do here?
Substitute MC delta T into Q.
So I've got MC delta T equals I squared R T over J. Right? That Q equals that Q. Therefore, this equals this. So far? Everybody's following me so far? Okay. 9 minutes left to finish this question. How do I isolate that T?
times by J, and then divide by I squared and divide by R.
Fantastic, Casey, good work. T equals MC delta T, oops, not J, MC delta T, times J over I squared, oh, not R, yes, it is, yeah, I squared R. So far, so good? Everybody's kind of following along so far? All right. So T equals M, which is what?
1,000.
1,000. C, back of the textbook. Same area we were in last time, so I'll find it for you. You guys can look it up in a second. Those of you that have a textbook, take a look. So it's actually on page 674. So it's just before the last thing we were looking at. So if you have a textbook under you, grab it and open it. If you don't, I'll get you sitting with somebody right away. 674. You got a textbook, peer over somebody's shoulder. Don't move beside them, just peer over their shoulder. So on page 674, you see that in the column A, that first column, they have specific heat constant. Do you agree with me?
Yes.
What is the specific heat constant for water?
1.
It's 1? For water, it's what?
1.
So that means that I need 1 calorie of heat to raise 1 gram of water 1 degree Celsius. Does everybody follow that?
Yeah.
So that 1 goes right here. What was my temperature? My temperature change was 80 degrees, correct?
Yeah.
And J is 4.19. All of that is over I squared, which I have as 5.318 squared times the resistance of 22 ohms. How long is it going to take to raise the temperature of water from 20 degrees to 100 degrees using the percolator that supplies 117 volts over 22 ohms of resistance?
538.747 seconds.
538.747, you said?
Yeah.
75 seconds. Fantastic. What do you have to remember when you're solving this guy? The way it looks? What's the most important thing? Anytime you have fractions?
Brackets,
Brackets. Where do I want those brackets?
multiply and divide.
Yeah, I don't need them on top because it's all multiplying.
Yeah.
But I definitely do on the bottom. It does not hurt to put them on top though. Open a bracket, 1,000 times 80 times 4.19, close bracket, divide, open bracket, and whatever else. Yes.
So for when we did the MC times our change in temperature, up at the top we had that it's, I think the C's are calorie over
Grams degree Celsius.
yeah, but where is that?
Right
Like,
here.
it should be
It's on here.
one, but like,
So then the Celsius cancels out, and the grams cancels out, so it leaves you with.
we did 1 divided by,
Well, no, you're not dividing. Those are units only. Those are just units.
oh, this isn't,
No, there's numbers that aren't there. They're just units.
okay.
Yes,
So the 4.19, should we have another times sign there in between the 80? Because it's times and all that other stuff?
Do I need the times anything when I put brackets? Do I need time symbols?
No, I guess not.
No, it means multiply, doesn't it?
Yeah, but I thought that you had to multiply all that times.
Jeffrey,
I can't get the answer.
are you dividing by, did you put the bottom in brackets?
Yeah, but I put them in separate brackets of that.
No. Jeffrey, you have to do this. You have to have brackets on the bottom. Any other questions or concerns?
How did we rearrange our questions to get just T? I know we arranged them so many.
Lexi? Watch. This has to multiply up there,
Oh,
and this has to divide down here. Okay, so you guys are
okay.
opposites, correct? Did you follow that?
Yeah.
These questions are a lot of fun as well. There's lots to go with them. They're 6 and 7 mark questions because there's lots to do in them, but they're fun to work with. Did you get it?
Yeah.
Okay. This section's good. You're gonna like this section too. If you like the last section, you're gonna like this section. Okay, it carries on. We still do a bit of circuit work in this one, because eventually we're getting to power, but they're not the complicated circuits, they're the easy ones. All right?
If you want to do it before this year.
Any questions or concerns? Page 452 has 2 problems. At some point today, before Tuesday, go through problems 1 and 2 on page 452. Write that down.
Well, what did you?
Go through them before Tuesday, please. And those of you that don't have a textbook, you gotta look at that, take a picture of it before the end of the day. 452.